Hello, everybody. My name is John Williams. I'm chair of the RAMIRAN 2020 Organising Committee, and it is my pleasure to welcome you to this webinar this morning. If times were different, we'd be meeting in Cambridge this week, but with the wonders of technology, we are able to have this excellent alternative. I'm sure many of us have experienced some technological difficulty over the last few months when doing these meetings, so please be patient with us, especially as we are hosting people from around the world. Before we get going on the meeting itself, I'd just like to go through a few housekeeping rules. Everybody will be muted, all the delegates will be muted during the meeting, but we will be taking questions at the end of each of the presentations. So if you want to ask a question, hopefully you can see there's a questions tab in the dashboard on the screen there, and if you could put your question in there, we will answer it or put it to the panelists. It might well be that we end up with lots more questions that we can ask during the time, bearing in mind the number of people that are joining the webinar, but we will log the questions, and it may be that the speakers get back to you after the event with the answers. I should also point out that the session is being recorded, and we will make the recording available later, probably on the RAMIRAN website. There is a short survey which we'll ask you to fill in after the end of the webinar, and it'd be helpful for us if you could fill that in. Grand. So we have the agenda for the meeting, and I'm very excited about the speakers that we have for us today. Over the next hour and a half or so, we have some presentations, excellent presentations, covering many important aspects of the management of organic materials. Zhaohai Bai, we're very lucky to have Zhaohai Bai from the Chinese Academy of Sciences, who's going to talk about nutrient use efficiency from a Chinese perspective. We've also got Karl Richards from Ireland, from Teagasc in Ireland, who's going to be speaking us about the important topic of reducing gaseous emissions from manure, and Bhogal from Teagasc in the UK, who's going to be speaking to us about the soil carbon benefits of organic materials. And finally, Dave Chadwick from beautiful North Wales, from Bangor in beautiful North Wales, will be giving us some information on a Global Research Alliance manure management network. So an exciting and enjoyable program awaits, and I'd like to start by handing over to Professor Zhaohai Bai from the Chinese Academy of Sciences. Thank you, Zhaohai. The floor is yours.
Thank you, John. My name is Zhaohai Bai, coming from China. I'm working in the Chinese Academy of Sciences. My topic is mainly related to the integrated assessment of crop and livestock production at the farm scale and also at the regional scale. We are also exploring options to implement nutrient management in the system, and mainly related to the manure management. And I'm very glad to join the meeting. Okay, so the title of my presentation is Contrasting Nitrogen Use Efficiency in Animal System and Options to Improve. Next slide. And there will be 4 contents. First is to briefly introduce the changes of nitrogen use efficiency and use pig production as example. Then I will show the transition of livestock production system in China, and to briefly introduce the options to improve nitrogen use efficiency. There are 4 different contrasting pig production systems in China. So we have backyard system, traditional system, medium-sized system, industrial system. They are not only different in size, but are also different in the slaughter time, feed management, and mortality, manure management. For example, the mortality will increase from the backyard system to the media estimate system. And here are some examples to show the traditional systems. So you will see this is the traditional backyard system, and for each family only have one or two pigs, and the main feed of these pigs are coming from the crop residue or kitchen waste, and the manure was returned back to the field. And this system usually have high efficiency, and in the right one is more unusual, but it still exists in only few villages, that they are sometimes using the chicken manure or even human excretions as part of the feed to the pigs. But from the nutrient cycling, I think it's a high efficiency way, but not everyone will accept it. And we also have industrial system. Here's pictures to show the industrial system. It's quite large and a very fancy technologies or facilities use precise feeding and a lot of concentrated feed, control the air temperature, this kind of issue. And another thing is that at the bottom right, you will see the big gray ones. That's the big pond for the manure storage. And a lot of these pig farms rely on evaporation or leaching to get rid of these problems. And sometimes of these manure can directly leaching or through runoff go to the water courses and cause a lot of environmental problems. And in the past, there were great industrialization of pig production system in China. So in the past, most of the pig production was occurred in the backyard system, but currently most of them are produced in the medium and intensive industrial systems. And how will this impact on the nitrogen use efficiency for pig production system? First, we need to define the nitrogen use efficiency, either at the national level, herd level, or at the system level. And our results to show that from the 1916 to 2010, we have found that the nitrogen use efficiency at the fattener level has been slightly increased, but at the system level, the nitrogen use efficiency has dramatically reduced from around 50 to only around 10. And this is mainly caused by the industrialization and the poor manure management. And this also lead to the quite high nitrogen losses from the pig production system. So through the industrialization, we found that the nutrient recycling in the traditional system has been broken up in the industrial systems. Most of the manure was going to the environment, and so it reduced the efficiency. It increased its reliance on the external nutrient input. And you will see that the pig manure nitrogen recycling rate has, recycling to the cereal field was decreased from 50% to only 6%. It has been reduced a lot. And most of these losses was occurred in the housing and the storage places, and during the discharge or ammonia emission and other losses. These accounted for major of the nitrogen losses due to the very poor manure management in China. So you will see from that there's only a few proportion of the manure was recycled. And this is not only happening for pig production, it's happening for the whole livestock production in China, and that's what we call the livestock transition. So in the past, the main purpose of livestock production is not only to produce the protein to the human, but it's produce or provide nutrients to fertilize the cropland to produce enough crop that supply the basic needed energy and protein for the people. Because at that time, the China was has lack of enough food, and produce manure to produce enough cereal food is more important than produce meat. So there's a lot of campaign or policies trying to raise the status of the livestock production. And in the past, livestock production was once an honorable thing, and it's very important. And because it can turn the non-edible crop products into the meat and also into the manure to fertilize the crop, fertilize the soil, and produce enough crop. And also, it's important source for income of family. In the past, if you only have 1 or 2 pigs per family, it's enough to support 2 or 3 the tuition fee for 2 or 3 children to go to school. So it's very important. But currently, the income of 1 head of pig, it's almost negligible because it's giving the income increase in the society, and also because of the marginal profit of the pig production. And also, the livestock production can provide the draft for transportation or ploughing the fields. So we find the livestock transition in China in terms of changes of animal number, because you will see that the total livestock unit has almost tripled, and also in terms of the production structure. So you will see that the transition was occurred through the structure is then from the mixed system and now to the land-lease system. So total number of livestock units in the land-lease system increased by 70 times, and also it changes from the ruminant animals that can turn the non-edible products to the meat, and to the change to the monogastric animals, pigs and layers, that high rely on the concentrate feed. And this transition means that loss of many functions of livestock production that we have gained in the past 3,000 years. And this transition only occurred maybe less than 30 years. Now the main purpose of the livestock production is to produce enough protein for the human in China. And this transition also caused, as I just introduced the case of pig, that has reduced the manure recycling rate, and also increased the external reliance on new nitrogen input, such as fertilizer and also imported feed, soybean. That's from US, Brazil, and Argentina, and it's also under controversial because there's severe deforestation in these countries. And also leading to quite low of the nitrogen recycling rate. It is in the whole system. And you will see that there was slight contributor to the improvement of nitrogen usage at the herd level. So you will see it's interesting to see the changes between 2000 and 2010. So you will see that nitrogen usage at herd level was increased, but decreased at the system level. That means there's dramatic reduce of manure nitrogen recycling to the system. And this has caused a lot of environmental problems, such as greenhouse emission, ammonia emission to the air, that caused air quality problems, and also nitrogen losses to the water course, that caused the eutrophication problems. And how to improve this situation? So here I also use production as an example. So in the right, you will see the systems, and in the left, you will see the options we have studied to improve the systems. First, we think that we can implement the low emission housing emission that has during the housing and during the manure storage that has low ammonia emission. And S2 is to improve the manure management and the fertilizer management. That means recycling the manure and to substitute the chemical fertilizer. S3 is that totally ban discharge of the manure to the environment without treatment. S4 is to the herd management, that trying to reduce the improve the mortality and other issues that we have need very little amount of soil that have additional feeding requirement. And S5 is the precision feeding of the pig and soil animals. And S6 is the combination of all 5 solution scenarios. And here is the results. The left is shows the total changes of the losses we can neglect, and in the right you will see the changes of the total losses in different scenarios. And you will find that actually from S1 to S5, they are very slightly contribution to the total nitrogen losses. But you will see the passes of nitrogen loss are varied greatly in different scenarios. This was like a concept for nitrogen gas in pipe with a lot of holes. So for example, if you take S1 that to reduce ammonia emission in a housing system, we have found that the ammonia emission has been reduced a lot, but discharge loss follow up the manure management chain has increased a lot, because you have preserved nitrogen in the previous stage, but in the later stage, this preserved nitrogen will losses rate will accelerate. So the only solution is to show the take the whole manure management chain options to reduce the nitrogen losses and trying to improve nitrogen efficiency at the whole system, and it's the only solution. Problem is in China that next one. Yes, you will see that this has strong impacts to improve the nitrogen efficiency at not only at the factory level, herd level, but also at the system level. So it will be working to improve the nitrogen efficiency. The problem is in the past, before 2015 or even 2017, the government was not paying too much attention to the problems of manure management, but things has been changed now. So our President Xi and also our minister has paid a lot of attention to the pollution of livestock production and paid attention to trying to improve nitrogen use efficiency. And into this, we also get a project working on reduce ammonia emission from the animal production system. The whole aim of this project is trying to develop technologies to trying to reduce ammonia emission by 50% in the whole manure management chain. And here we are aiming to develop technologies in housing, treatment, and application, trying to develop different technologies to improve the nitrogen efficiency and trying to reduce ammonia emission. And we also take the chance to do the whole county scale demonstration to implement a lot of facilities in the whole county, trying to achieve the mitigation of ammonia emission and trying to improve nitrogen efficiency at the whole county. It's a very big county, and it can maybe a big example for the whole world. And here is the conclusions. So we can see that nitrogen use efficiency was contrasted at a different scale and a different system due to different management practices. Nitrogen use efficiency was also increased at the herd level, but may decrease at the system level due to the poor manure management and the decoupled feed and pig production in China. In the livestock transition towards to industrial system and monogastric animals has greatly changed the nitrogen cycling and the nitrogen use efficiency in China. And the improved system nitrogen use efficiency relies on the whole manure management chain options and trying to recoupling of feed and livestock practices. That's all. Thank you.
Zhaohai, that was brilliant. Thank you very much for that excellent overview of the situation in China. You have many challenges with the manure management systems in China, and it's excellent to see how things have changed over the years. We have a couple of questions, and so please, if you want to ask questions, put them into the question box there. We have one there which would like to know how the nitrogen use efficiency is determined. What are the how do you quantify the nitrogen use efficiency?
Well, at the fattening level is defined by the output and the total feed nitrogen input. And it's also the same at the herd level, but we also include the feed requirement for the sows and the bulls and for all the backup animals. But at the system level, it's a little bit different. So we not only consider the nitrogen output by the animals, but also by the other output. And also we also consider all the new nitrogen input in the system, like the feed import from abroad, the fertilizer applied to the domestic crop production, and biological nitrification, deposition, this kind of import as all considered.
That's an excellent answer. Thank you. It shows how complicated it is and all the how far the nutrients come into the system and the impacts that feed, particularly the feed imports, and what the impact that's likely to have on the way that agricultural practices are governed in other parts of the world as well. So that's really interesting. Thank you. I have another question here. What is the fate of the oh, sorry, hang on. I'd like to ask, what is the fate of the manure treated in the facilities you last described? Weren't able to catch that. So yeah,
okay. Yeah. So in the last slide, it's about the manure composting machine. Because in the past, for the manure composting, you have a lot of ammonia emission losses, and its processing rate time is quite slow. Now our group developed a new machine it's a vertical machine, so manure feed from the top, okay, then go eventually by the gravity to the bottom, and all the ammonia emission has been trapped by another tank with a lot of acid leakage. So we trap all the nitrogen emitted from the system and increase the treatment efficiency. And the final product, the composted manure, will be used to produce the formulate fertilizer that can apply to the local crop production system. So they were trying to increase the recycling of the nutrient at the regional level.
You can see.
That's brilliant, Zhaohai. Thank you very much indeed. One last question. What regulations are in place currently to reduce nitrogen losses from livestock production in China?
Well, yeah, there are some regulations, but it's not related to nitrogen losses. I think currently there's only one regulation related to the two, maybe. Yeah, there's absolutely no discharge to the water system is not allowed, and you have to have new facilities to try to reduce ammonia emission. But regulations are not that strict now because of the African swine fever. And I think one important policy currently now is trying to increase the manure recycling rate up to 75% by this year. This is a regulation by the Ministry of Agriculture and Rural Affairs. This is, I think, is very powerful regulation.
Great. I'll just ask this last one because I missed this one at the beginning. Our system is I'm getting used to the system now, but are cost analysis included in the development of the systems? For example, the production of alternative fertilizer products like struvite and the like.
I don't understand this question, and no, I think we don't have the cost analysis.
Right.
Okay. Yeah.
Brilliant. Okay. Zhaohai, there's lots of other questions that have come in. Unfortunately, we've run out of time. What we'll do is we'll save those questions, and if it's okay, we'll pass them on to you, and then you can reply to them at your leisure, if that's okay. And hopefully everybody asking the question.
Yeah. Okay. Brilliant. Thank you. I'll be top of the camera. Yeah.
Thank you very much, and see you next year. Brilliant. Thank you. Excellent. So on this world tour that we're on, we move from China over to Ireland, where I'm delighted to introduce Dr. Karl Richards, who is Head of Crops and Land Use and Environment at Teagasc in Ireland, who's going to speak to us with an Irish perspective on reducing gaseous emissions from manure. Brilliant. The floor is yours, Karl.
Thank you very much, John, and good morning to everybody. Maybe just to slightly correct John, I'm head of the Environment, Soils and Land Use Department and not the head of crops in Teagasc. So Teagasc is the Irish Agricultural Food and Advisory Service. So we encompass research, advice and education. Me, myself, I'm, I suppose, a soil scientist who's been working for many years on nitrogen cycling in soils. So if we can put up the first slide of the presentation, I will turn off my camera. So this morning I'm going to speak to you about, I suppose, the Irish perspective on reducing gaseous emissions from manure. Hopefully it's changing. Okay, so in terms of the challenges that we're facing with the abolishment of the EU milk quota back in the sort of 2012, 2013, the Irish dairy industry targeted expansion as for the first time in a number of decades we're able to produce more milk as we have been constrained quite heavily by European milk quotas. So the industry developed an industry plan for the doubling of milk production in the country. At the same time, we have very real challenges in terms of gaseous emissions, be that greenhouse gases from agriculture or ammonia emissions from agriculture. And the targets that we've been set have been, agriculture accounts for 32% of our greenhouse gas emissions nationally, which is a very high proportion compared to many other EU and even non-EU countries. And obviously agriculture accounts for most of the ammonia emissions, about 99% of ammonia emissions. Our government has set quite strict targets to achieve by 2030, and indeed our recent government has increased the aspiration of those even further. So the country as a whole is targeting a 30% reduction in greenhouse gas emissions by 2030, with agriculture accounting for about 10% of the reductions. So to reduce emissions by 10%. So to go from 20 megatons down to about a range between 17.5 and 19 megatons. But agriculture also has to deliver the carbon sequestration requirements, as we received a 2.7 megaton per year carbon offsetting allocation as part of the Paris Agreement. So agriculture needs to deliver on both of those. With our new government, it looks like the aspirations are going to be to reduce greenhouse gas emissions by 70% by 2030. And it's our understanding that carbon sequestration and enhancing that will become a major part of that target. In terms of ammonia emissions, we have a 1% reduction over the period 2020 to 2030, and then 5% onwards. While that sounds very small, it is quite challenging based on our grazing grassland ruminant systems that we have. And we also need to be aware that ammonia mitigation can be synergistic or antagonistic with greenhouse gas mitigation, and I'll talk a little bit about that later. So really, policymakers were wondering, well, what can we do to achieve these targets? And I suppose what I'm going to guide you through in the next sort of 10-15 minutes is, I suppose, our approach to helping policymakers to develop policies to achieve the targets that they have signed up to. And these are principally identifying the measures that can be used, and that's both the efficacy of an individual measure and its cost, but also to look at the likely adoption rates by farmers to give us an estimate of the total mitigation potential of that measure. So as I mentioned, agriculture on the left-hand side of this graph is greenhouse gases, and you can see the breakdown. Sort of 2/3 of our greenhouse gases relate to methane emissions from animals, so enteric fermentation, And then the other losses include nitrous oxide from managed soils, primarily sort of fertilizer, but also some grazing returns. Manure management also accounts for, about what is that? About 10% of emissions from nitrous oxide and methane associated with manure management. On the ammonia side, on the right-hand pie chart, you can see that primarily most of the ammonia emissions are associated with animal manure, to do with 48% to do with manure management, housing and storage, land spreading accounting for about 30%, and grazing a further 12%, and less than 10% of our ammonia emissions coming from fertilizer, primarily the use of urea by farmers. So just a little bit of data, recent data. So as I mentioned, from 2013 onwards, our agricultural industry has been expanding dairy production. So the orange line is milk statistics from our central statistics office, and you can see that we've had about a 40% increase in milk production in the period 2013 to 2018. At the same time as that, we know that we have reduced the carbon footprint of our milk production by about 13%. So I suppose we have somewhat of sustainable intensification in that we are reducing the footprint. But unfortunately, we can see from our National Farm Survey, from the recent sustainability report published in 2019, that emissions of both greenhouse gases and ammonia have increased by about 12% over that period of 2012 to 2017. So while we are improving the efficiency of milk production, it isn't completely offsetting the increases in greenhouse gas and ammonia emissions. So we still have a major issue to overcome. We can also see that over that period, nitrogen use efficiency has increased slightly by 2%, but nitrogen surpluses have also increased slightly by 12%. When we look at the performance of different farming categories, so the top performing farmers have the lowest emissions intensities, but they also have the highest emissions and the highest nitrogen surpluses. So while they are efficient, they really do need to apply measures to reduce nitrogen surpluses and emissions even further. So it really is important to disentangle the concepts of efficiency from absolute emissions. And from a gaseous emissions point of view, absolute emissions is what the environment sees. So we really do need to focus on that. Whereas a lot of the time farmers and I suppose marketeers and that focus on intensity, which does complicate our discussions somewhat. So as I mentioned, so this is our greenhouse gas emissions from the year 1990 up to about 2016. It's a little bit out of date, and sorry for that. So the black line is actual emissions, and then you'll see a series of 6 lines which are associated with different scenarios of what our industry might look like up to 2030. This was carried out by colleagues in our rural economy section who used the Fabry Ireland model to estimate what the national herd would look like depending on different scenarios such as Brexit, WTO, etc., etc. So there's a range. So the key point here is that there's a range in where our industry could end up, and that range is about 2.3 megatons, which is a sizable difference. At the moment, it looks like we're on course for the between S1 and S2. If we end up at S4, it's going to be incredibly difficult to achieve the targets as indicated by the minus 10% target line below. And as I mentioned, our government is looking at further increasing the reduction targets for 2030, and it's unknown at the moment what impact that's going to have on agriculture. But as agriculture accounts for 30% of our emissions, it is going to have an impact. So we've looked at a range of scenarios or a range of measures. We've divided them into 3 groups. One is on reducing actual methane and nitrous oxide emissions from agriculture. And this is looking at lowering emissions from animals, from manure, and fertilizer, etc. The other area is in the land use change and forestry, and that's around carbon sequestration. And as I mentioned earlier, Ireland has the ability to offset emissions by 2.7 megatons per year. And then the final area is agriculture's contribution to improving energy efficiency and offsetting the use of fossil fuels in the country through biofuels, bioenergy, biomethane, biogas, etc. For the purposes of today, I'm just going to focus on the agricultural measures and specifically on the manure-related measures. So what we've done is we've produced what we call a marginal abatement cost curve. This curve indicates the efficacy of a measure. So the width of a bar on the y-axis indicates in kilotons of carbon how much an individual measure that we estimate can reduce greenhouse gas emissions. On the y-axis, you'll see the costs running from negative costs of 600 euros per kiloton of carbon reduced up to an actual cost of 200 euros per kiloton of carbon reduced. You'll see measures on the left-hand side of the figure are generally efficiency measures. They save farmers money and at the same time they reduce emissions. One of the challenges with that is that by improving efficiency, often farmers can increase their activity level, thereby increasing the amount of product they produce and leading to a net increase in emissions. Within this marginal abatement cost curve, there are areas where manure and manure management play a role. On the left-hand side, we have the Dairy Economic Breeding Index, and this is an index of our animals around the genetic merit and a range of other animal factors in there. So by improving the genetic merit of our animals, we can optimize nitrogen nutrition and reduce nitrogen excretion and optimize milk production, etc. Extended grazing also has an impact in that you reduce the nitrogen losses associated with the manure management chain as animals are out on pasture for longer, and generally the emissions from grazing are lower than within the manure management chain. On the right-hand side, you'll see a number of dietary measures. This would be reducing the crude protein in animal diets, and then you have above the x-axis, you have the measures that include amending slurry with different additives, and I'll talk a little bit about that later. And you've also got low emission slurry spreading, which, while it is the most costly measure for reducing greenhouse gas emissions, you'll see a little bit later on, it's the only show in town when it comes to reducing ammonia emissions, and that's why it's included within our MAC. So this curve, which we published back in 2018, is based on the efficacy of an individual measure. So that's how much greenhouse gases it can reduce, multiplied by an activity estimate. And that activity estimate has been derived based on expert opinion and with discussion with policymakers in terms of what they think policy and regulation might deliver. Part of it also comes down to the practicality of an individual measure and the costs associated with that. So in more recent times, again, so ammonia has been a really key issue in Europe for a number of decades, and it really hasn't impacted in Ireland very much to date, but that is changing. There is an increasing emphasis on ammonia emissions. When we look to Northern Ireland, so the northeastern corner of Ireland, which is within the UK, we see that there is a move by the environmental regulators to protect sensitive habitats from ammonia deposition. And this has led to planning permission refusals for farms, for farmyards and for farm buildings. And ultimately, this is looking like it's going to constrain agricultural production in that region quite dramatically. The top headline there is the Northern Ireland Environment Agency chief admits ammonia is becoming the new nitrate. So for those in Europe, the Nitrates Directive is one of the key, I suppose, agricultural regulations limiting or impacting on the intensity of agricultural production in Europe. So it looks like ammonia could become even more stringent than the Nitrates Directive. So this has a lot of people worried. The impact in Southern Ireland may not be as great as in Northern Ireland because our agricultural systems are quite different in terms of the length of our grazing season. In the Republic of Ireland is very long. Typically, you're talking 220 days per year animals are grazing fields, whereas in Northern Ireland, that's much more likely, probably around 150 days. So about half of the year or less, animals are out in the fields grazing, which means there's an awful lot more manure generated. So this again is another projection of ammonia emissions, and you'll see the black line again is actual ammonia emissions, and then we have the 6 scenarios around where ammonia emissions might end up depending on the size of the beef and the dairy herd, depending on, as I mentioned, a range of different factors. What is quite clear is the target of 107.6 kilotons in 2030 is quite a bit below all of those scenarios. And this is a legislative requirement. Currently, Ireland is in breach of the National Emissions Ceiling Directive and is producing a plan to, come into compliance in the period 2020 to 2030. That plan that is currently going through government at the moment is being based on another marginal abatement cost curve that we have produced within our organization. This is the current version of it. It's due to be published in the next couple of weeks. And what you'll see primarily is that low emission slurry spreading of cattle manures is the single largest measure within that to reduce ammonia emissions. As I mentioned earlier, that accounts for about 30% of our national ammonia emissions. So it is one of the key areas. Obviously, changing from urea to urea with a stabilizer, such as NPPT, so a urease inhibitor, can reduce ammonia emissions quite dramatically. And that is also being considered. What you will note is, though, we didn't include changing from urea to ammonium nitrate-based fertilizers. And this comes down to, I suppose, the impacts that would have on our greenhouse gas emissions. Within Ireland, we have country-specific emission factors for different fertilizer types, and the ammonium nitrate emission factor is 1.49%, which is 0.49 above the IPCC default, whereas our urea with NPPT or urease inhibitor is down at 0.3 or 0.4%. So there's a huge greenhouse gas, primarily a nitrous oxide emission factor difference between those fertilizer types. And we then have a range of other more expensive options around adding amendments to slurry. And those amendments I'm going to look at in a little bit more detail. Currently, they are not practiced in the country. This is based on, I suppose, research findings, and the acceptability to farmers is a little bit unknown, as there is quite a bit of sensitivity around impacts that we might have on the, I suppose, the safety and the food quality of the products that we produce. So next slide. So currently we're carrying out a range of new research. Just give you a couple of little highlights here. So primarily what we're trying to do is refine national emission factors for new measures. So these are new things that we can add into our marginal abatement cost curves. As I mentioned, slurry additives is an active area. Slurry acidification is also another active area. And then dietary additives, where we can reduce the methane emissions directly from the animal and from the manure management chain, are also being investigated as part of new research projects. On the right-hand side, you'll see we have a slurry storage facility, a mesocosm facility, where we can look at the effect of different treatments on sort of representative slurry stores. So these are simulated storage tanks of 1 meter cubed capacity, where we can simulate different slats or mats on slats. We can cover them with a chamber, as you can see in the top right-hand photograph, and measure ammonia, methane, and nitrous oxide emissions coming from those tanks. In the graphs below, you'll see some early results from some of this work, where we've looked at a range of different additives. The top graph is ammonia emissions in grams per meter squared. You can see the grey bar is the control, and then we've got a number of additives: acetic acid, alum, which is aluminium sulfate, I think. It's a leftover byproduct of the water treatment industry, ferric chloride, and sulfuric acid. And you can see certainly all of those additives have a dramatic reduction on the ammonia emissions during storage. In the bottom graph then, we also find the same effect on methane. So those are cumulative methane emissions in grams per meter squared. And you can see again that those same additives have a dramatic effect on reducing the methane emissions from storage. So additives work, and I suppose what we're trying to do now at the moment is do further refinement around those additives in terms of addition rates, etc. But we also need to consider what the I suppose subsequent impacts are when we use that manure. So that's during storage. So storage, as I mentioned, accounted for about 48% of our national ammonia emissions, storage and housing. So this would dramatically reduce that. We've also considered the impact that those additives have when we go and spread that manure on the soil. So this is some ammonia emissions work that was done. And again, this is a very active area of research. There was a treatment where lime was added to the slurry to stabilize, I suppose, stabilize the manure in terms of its biological quality, and that dramatically increased emissions. But if we look at the next line down, which is the black diamonds, that is our control, and all of the other additives reduce the ammonia emissions from the field as well. I don't have it here, but we're also looking at the impact that has on nitrous oxide emissions coming from the applied manure. But we can see that the alum and the ferric chloride reduced ammonia emissions between 60 and 80%. So again, we get a nice added effect of when that manure is applied to the soil. So again, one of the areas I mentioned is food safety. So we are looking at the impact of these amendments in a new project that they have on the quality of the grass that is grown, but also impacts on the soil biology and the soil health to ensure that there's no trade-offs occurring there. So that's some of our current areas of research. In terms of incorporating these measures into the inventory, policymakers often have a view that, you know, the measures need to be easily incorporated. And a lot of the time, some of the main factor that inhibits the incorporation, it's nothing to do with the science that we're doing in terms of emission factors and that. That's all well understood, it's published and accepted in the literature. The major issue is around collection of activity data. So how can we quantify how many farmers use a certain mitigation measure? The more complex the mitigation measures become, the more complex the requirements for data collection becomes. So currently in our organization, we're looking at trying to expand our National Farm Survey to generate some of these data requirements. But policymakers often seek easily quantifiable measures, which, you know, we all know, you know, there's not that many of them, and they often revolve around total manure use or total stocking rate or total fertilizer use. But even knowing how much slurry in the country is spread by a specific slurry method, and what sort of tanks are used, if people start to use additives in slurry, how do you verify and report that activity data? And more recently, within the National Emission Ceiling Directive, and it's an area that we haven't particularly devoted much resources to, is around the air quality. So the new National Emission Ceiling Directive setting limits for methane and NOx, which we know are really important emissions coming from slurry. And we do need to refine our emission factors around those specific gases or air quality pollutants coming from agriculture. So where are we going to now? So while we know what needs to be done, it really is important to transfer this knowledge onto farms. So within Teagasc, we've established a new Signpost Farms initiative. This is a series of 70 farms across all of our farming sectors. And the challenge here is to implement the marginal abatement cost curves that I have just highlighted to you, and to look at potential feedbacks, both positive and negative, within those implementation, and to improve adoption through demonstration on farm and getting that peer-to-peer, farmer-to-farmer knowledge exchange. We've also got Nutrient Management Planning Online, which is an online nutrient management tool, which automatically generates field-specific nutrient advice based on laboratory analysis of soil tests and farmer field-by-field data. So once a farmer inputs their field-specific data, that's retained in the system for the future, and the laboratory results are automatically imported into the system. So this is providing advisors and farmers with maps, nutrient requirement maps for their farms, and currently we're about to develop a mobile app that will further help farmers to optimize soil fertility on their farms. We also have Pasture Base Ireland, which is, as we are 90% grassland in Ireland, we need to know, or the challenge is to know how much grass is growing and what the future grass or predicted grass growth are going to be in the next 10 days, 2 weeks. So again, there's a lot of developments around this. There's about 2,000 farmer users of this system at the moment, where they're inputting weekly grass covers or the amount of grass on each of their fields. And then this has been used with a grass prediction growth model in the end. And also we developed what we call the Carbon Navigator, which is a tool, a knowledge transfer tool, again, to help farmers to assess where they're at with their emissions from their farm, and to test what impacts different measures would have on improving the efficiency of their systems and reducing greenhouse gas emissions. So this tool is used across all Irish farms by our Food Marketing Board, Board BIA, and it was a tool developed within Teagasc. So currently our national actions, we have a number of industry initiatives. We have a Dairy Sustainability Forum. We have the Signpost Farms, as I mentioned. Some of our dairy co-ops are now introducing sustainability bonuses, where farmers receive an additional 1 or 2 cents per litre of milk, depending on their delivery of certain sustainability requirements. Within the policy area, we have our climate action plan. We have our agricultural policy called Ag Climatize, which is being finalized at the moment, and that will set specific targets for the industry in terms of reducing both greenhouse gas and ammonia emissions to meet the 2030 requirements. And we also have the nitrates derogation, and the current review that was carried out this year is integrating, as it has in the previous derogation review, integrating climate actions into that, such as the mandatory use of low emission slurry spreading on derogation farms, and also the use of stabilized urea or protected urea, or urea with MBPT. So again, you're starting to see a convergence of policies into our main agricultural regulation, which is the nitrates derogation. And then finally, on the research side, I mentioned some of the projects. We're in the process of scoping out a centre of excellence for gaseous emissions from agriculture. We're developing a carbon infrastructure across the signpost farms and some of our research farms, which will include a number of new agricultural ICOS sites using eddy-covariance technology, supplemented with a large amount of soil sampling and monitoring. And then we're looking at a range of measures to abate emissions and to enhance carbon sequestration. So moving on to my final slide. So to conclude, there is an increasing emphasis on reducing gaseous emissions, and policymakers are looking for assistance in developing regulations and policies. We found the marginal abatement cost curve a very useful approach to prioritizing measures, and we found that they have been directly inputted into agri-environmental policy in Ireland, and you know, within our policymakers, even up to the level of our Prime Minister. I think if you mention the Teagasc MAC, he will know what you're talking about. There's a need, the minute we publish a MAC, it's out of date. So there's a need for continual improvement and continual revision of the MAC. And that's both in terms of new measures, but also in terms of adoption rates. And that's, as I mentioned in the previous slide, this is where policy convergence is helping, in that previously on the greenhouse gas side, we had to estimate what we thought the likely adoption rates are going to be. In the Ag Climatise policy document, they set what those adoption rates are going to be, and we can use those within our scenarios. But there is also a need to consider the multiple dimensions of measures, not just in terms of air, greenhouse gases, but in terms of water, soil quality, biodiversity, and also social, economic, and acceptability criteria for farmers as well. So we have significant mitigation measures. The mitigation potential exists, but it's only on paper. And this is where we are working with farmers and farming organizations to improve the communication and implementation of actions on farms. But you know, behavioral change is a significant challenge, and we know that within our farming community. And the hope is that our signpost farms will demonstrate the practicalities of these measures, the efficacy of them in terms of cost savings, etc., and facilitate peer-to-peer learning, farmer to farmer. So John, with that, I'll finish, and thank you all for your attention.
Karl, that was brilliant, mate. Thank you ever so much. That was a fantastic presentation, and absolutely demonstrates the importance and the complexity of the issues we have to deal with when it comes to handling this wonderful material called manure. Particularly the importance of not looking at things in single issues, and the importance of them dealing with as many of the dimensions as we possibly can. The fact that if you put a hole, you fill one hole to stop the nitrogen coming out, as our coming out of another one, and all the other impacts on soil and biodiversity and everything. Absolutely fantastic. Not surprisingly, we've got loads of questions, and I'm afraid we won't have time to go through them all. But I'll start with one from a colleague of ours in DEFRA in the UK over here, who's interested in the linkage between emissions intensity and absolute emissions. What steps do you think could be taken to decouple these to some extent?
Yeah, so I think one of the keys is nitrogen. So we can improve nitrogen use efficiency through increasing uptake of nitrogen is one thing, but we can also increase it by reducing nitrogen inputs. And one of the keys for that, and we do highlight it in a number of our measures, is optimizing soil fertility. So currently about 60% of Irish soils are suboptimal for pH, P or K. So therefore nitrogen isn't being used efficiently. The problem though is if you don't improve that efficiency, you're using nitrogen as a band-aid. So really the challenges are around reducing absolute nitrogen inputs into those systems. And some of that really comes down to, like, we can demonstrate it as much as we can, and the effects, etc. But when you introduce a regulation, that often has a much more dramatic effect on farmer action. So the real challenge is, it's the problem. So on the efficiency side, so if we improve the breeding index of animals, it means farmers can produce more milk with fewer animals. That means they can potentially increase the number of animals and increase their milk production, although the carbon footprint of that milk will be slightly lower. And so, as I said, milk production increased by 40%. We didn't see a 40% increase in emissions. I think it was a 12%. So, it's sort of similar to COVID. It was flattening the curve a bit, but unfortunately, flattening the curve for greenhouse gases isn't enough. We need to do a downward and quite a steep downward trajectory with greenhouse gases. So really is challenging. So what we're doing is focusing on measures now that will deliver absolute reductions.
Brilliant. That's great. Yeah, no, fantastic answer. Thank you very much for that. Another one relating to ammonia emission reduction. What is the impact of adding more iron and aluminium to soil from treated manure? I guess this is another one, wondering what the impact is on soil quality of ammonia emission.
And as I mentioned, it is an active area that we're looking at. If you look at the literature, and again, look, it's been a few years since I looked at the literature, but in the US, they've been using alum as an additive in poultry sheds for quite a long time, primarily to sequester phosphorus and reduce phosphorus losses. But the estimates I remember at the time were that the amount of aluminium that you were applying to the soil is a tiny, tiny, tiny fraction of the total aluminium and iron reserves in the soil. So, but it is something that we do need to consider. And as I said, it doesn't take much to put a farmer off, or a dairy processor or a meat processor. If you raise the issues around residues and things like that, they run for the hills, and it just means they don't do anything, and we don't move from we don't move along the road of reducing emissions. So we've probably run out of time. I am happy to provide answers to the questions that you've received.
That's brilliant, Karl. Thank you very, very much for that excellent presentation and for answering those questions. As I say, we'll send those questions on to Karl. Apologise for the people who've asked the questions. I guess the answer is get in early because you've got a chance then. So thanks ever so much, Karl.
Thanks, John.
Grand. We're moving on now to moving from Ireland to Yorkshire in the UK on our world tour, and I'm delighted to introduce Dr. Anne Bhogal from Teagasc, Principal Soil Scientist with Teagasc over here in the UK, and she's going to talk to us about the soil carbon benefits of organic materials. Anne, the floor is yours.
Thank you, John. Morning, everyone. It's a shame we can't be in sunny Cambridge this morning, but hopefully what we've heard so far and what's to come will just give you a little bit of a flavour and a taste of hopefully what we might be able to do next autumn. Fingers crossed. So as John said, I'm a soil scientist. I work alongside John at Teagasc in the UK. And so I'm going to be talking about soil carbon benefits of organic materials. Okay, so I put this first slide up really just to demonstrate what I'm going to be talking about. Why recycle organic materials to land is really what RAMIRAN is all about. And we're all well aware of the benefits of doing this, not only from the perspective of closing those nutrient loops and returning nutrients back into the system to be used again in the most efficient way possible, but also from the organic matter benefits that these can give. And there's two aspects of the organic matter which I want to focus on this morning. Firstly, the way in which it can be used to improve soil health. And then secondly, I just want to talk briefly about soil carbon storage in the context of climate change mitigation. So, soil health and the importance of organic matter. We've, over the years, we've talked about soil fertility, we've talked about soil quality, And now the buzzword really is very much soil health, and it's being talked a lot about these days. So I thought I'd put a quick definition of what I mean by soil health. And it really emphasises the fact that soils are living, so that's the healthy part of soils. And it also emphasises the fact that we need to take a functional approach when we think about soil health, soil quality, and it's sustaining those functions in the long term that is important. And so if we take that functional approach, we can actually see that the majority of soil functions are actually driven by biological processes. And those biological processes are underpinned by soil organic matter decomposition. So organic matter is the driving force within soils, and therefore, not surprisingly, it's a key indicator of soil health. And so this little schematic that I've just put at the bottom of the slide just demonstrates this. Organic matter provides that food source for the biology, which drives nutrient cycling. But it not only drives nutrient cycling, it drives aggregation and the formation of good soil structure. Organic matter itself, through its cation exchange capacity, does that job. And also, together, this good soil structure and organic matter help with water relations, the regulation of water, the flow of water through soils and its storage. And then also organic matter is that important carbon store, so therefore involved in the regulation of atmospheric gases. So we all know the benefits of having organic matter in our soils. So the improved soil structure, water holding capacity, the infiltration, the biological activity and nutrient turnover, in turn leads to improved rooting, nutrient and water capture, reduces runoff and erosion, reduces waterlogging, and then that in itself improves our productivity, provides greater resilience in our systems, reduces flooding and emissions to the environment. And then ultimately, that reduces the cost base of the system. And so there are actually a number of ways in which we can improve organic matter levels. This are just some numbers to give you an idea of the magnitude of changes that we can achieve. This is a typical topsoil in the UK containing about 120 tonnes per hectare of organic matter down to 30 centimetres. And some numbers produced by Pete Smith and his team at Aberdeen some years back, just to show you the direction and magnitude of change of a number of different practices. So we can change our cultivation, we can move from a plough-based system to minimum tillage or reduced tillage or no tillage, and we can store a little bit of carbon that way in the topsoil. We can grow high yielding crops so that we can return more residue material back to the soils. But by far the biggest change we can do is actually change the land use. So here going from arable to grassland can cause the biggest change, but likewise if we go the other way we can lose quite a bit of carbon by ploughing out grasslands. But that aside, obviously in not all circumstances can we change our land use system. Applying organic materials is by far the sort of second best option that we have in our toolbox to improve soil organic matter levels. And it's particularly applying those bulky organic materials, the high dry matter materials, that have the effect. So here's just to give you an idea of the numbers involved. These are all solid manures applied at typical application rates equivalent to 250 kilos of nitrogen being applied, so to keep within the nitrate vulnerable zone rules. And you can see for something like a cattle farmyard manure, we can be returning anything up to about 5.5 tonnes of organic matter in a single application. Similar for composts. Broiler litter, because we've got more nutrients in that, we can't apply so much. So therefore our organic matter improvement is not, the potential for there is not so great. But there's a lot we can do, obviously, with bulky organic materials. For slurries and digestates and liquid manures, obviously we're applying a lot less dry matter, and we're probably looking at something of less than 1 tonne per hectare of organic matter applied with those materials. So we know that organic materials can improve soil organic matter, but do they all have the same effect? And this was actually recently discussed in quite an interesting paper by the soil biology team at Wageningen. And I've just put a quote here from that paper that basically says, yeah, we know that we can improve functions by increasing organic matter levels, but what we don't know so much about is the relationship between these functions and the quality of the organic matter that we're putting in. So we have questions like, do all organic materials behave the same, or are some better than others? Do they serve different purposes? So can we tailor what we want to do according to the organic material that we're applying? And in that case, what characteristics are important? What should we be looking for in that material? And then obviously, how much do we need to apply before we start to see the benefits? And these are key questions that are still outstanding, as we can see from this, this recent paper. But to just give you a bit of insight into this question, a piece of work we carried out a couple of years back now for the Waste Recycling Action Programme within the UK, looking at digestate and compost use in agriculture. We had a number of long-term experimental sites that had repeated additions of a range of different organic materials that you can see along the bottom of this chart. Some of them have been applied for just a few years, so 3 repeated years of application. Some have been applied for a lot longer, so up to 20 years of application. And so this chart basically shows the change, the percentage change in organic matter, topsoil organic matter, after these additions in comparison to a control treatment that received no organic materials but did receive recommended rates of bag fertiliser. And I wanted to draw your attention particularly to the 2 high bars. But firstly, just to say that obviously with 3 years of addition, the change is relatively small. You need to be applying these materials for a number of years to see some big changes in topsoil organic matter. But here you can see that green compost applied for 9 years, supplying 50 tonnes of organic matter, resulted in a virtually identical increase in topsoil organic matter to a farmyard manure applied for 20 consecutive years, supplying almost double the amount of organic matter. So the improvement in organic matter was much more rapid with the green compost. And we can put this down to the decomposability of the materials that we're applying. And so we measured this by looking at the lignin contents of the different materials applied. And so this chart just shows the lignin carbon content as a percentage of the total carbon content of those materials. And you can see that the compost had a lot more carbon in those more stable lignin forms compared to the farmyard manure. So it sticks around longer. It breaks down a lot slower, and so can build up those organic matter levels in the soils a lot quicker than a farmyard manure. But what about the other soil properties? Do we see a similar effect? And this was when it became quite interesting. So this next chart is a similar chart, but looking at the effect of the organic materials on microbial biomass, carbon within the topsoil. So again, this is percentage change in biomass carbon. And here you can see a very different picture. So you can see that actually the farmyard manure had the greatest change, 60% change in microbial biomass compared to the green compost at around 15%. change. And that is despite those two treatments having the same total organic matter content within the soil, so the same amount of carbon in the soil. Likewise, actually, when we look at some of the soil physical properties, this is change in topsoil bulk density, again with the same materials, and we would expect bulk density to decrease with increasing organic matter content. Soil becomes lighter, more fluffier, easier to work. And again, not quite so a bigger difference, but the farmyard manure coming out as having the biggest change in the bulk density compared to the green compost, even though those total organic matter levels were exactly the same. So we can see that actually it's not only quantity of organic material that we apply, but that the quality does have an effect. And so, as I say, quantity and quality matter. So for something like a farmyard manure, we could call that decomposable organic matter. These have high turnover rates. The retention of carbon is a lot lower, and so more is needed over a longer time scale to boost that functioning. But it does support a higher biological activity and has a greater impact on soil physical functioning, where this compares to a more resistant material such as compost, which has a lower turnover rate, so carbon retention is higher, and so you can improve those levels over a shorter time scale, and it does improve soil biological and physical functioning, but to a lesser degree to compare to something that's a bit more biologically available. So this is all well and good, but what impact does that have then on crop yields, which is what the farmer is really after, an improvement in his crop performance? And this has been a question that we've tried to be teased out over the years. What is the benefit of the organic matter in particular? Apart from the nutrients, we can account from the nutrients in the organic material that we apply and reduce our fertilizers accordingly. But what benefit does the organic matter have on crop yields? And again, a team from Wageningen tried to tease this out a couple of years ago at an IFS presentation. And they reviewed a number of meta-analyses on the subject. And they found that in those studies where nutrients could not be excluded, could not be separated from the organic matter effect, so the outer ring on this chart, they found that actually the yield effect was positive in all cases. So they could, but we couldn't actually say whether that was due to the additional nutrients that were being applied or whether it was due to the organic matter. In those studies where nutrients were controlled, and so we could exclude that nutrient effect, we saw a different picture, and that's the inner circle. And you can see that actually there was only 1 or 2 cases that showed a positive effect, the majority actually showing no effect of that organic matter per se, and some actually with a negative effect. And interestingly, the yield benefits were actually most often observed in tropical regions compared to temperate, with roots and maize compared to cereal crops, and with light textured soils compared to heavier textured soils. And to me, that points to sort of water supply, water availability, water accessibility benefit of the organic matter. And just to highlight this is going back to that study that we did for RAP. And this is just one of the sites, just a demonstration of the differences in yield. So again, these are the different long-term treatments. So a green compost applied for 9 years, farmyard manure applied for 20 years. And in that sort of 20-year period, there was probably only 2 seasons that we actually saw a statistically significant effect on yield. And in this case, in 2013, it was when we had a particularly dry spring, and the the winter wheat on the farmyard manure treatment benefited from that extra functioning of the higher organic matter content compared to the green compost. So we said that actually the yield effect is most obvious in those tough seasons. So the organic materials there are providing some resilience in order to cope with things like spring drought. Right, so just moving on then to talk about organic materials and soil carbon storage. There's no doubt that applying organic materials, and particularly those bulky high dry matter materials, will increase soil carbon stocks. And there's been a lot of work on this subject, a lot of papers published, a lot of meta-analysis. This is just one that was published recently. 200 comparisons gave a figure of between 200 and 1,300 kilos of carbon per hectare per year could be stored as a result of organic material applications. And looking at the literature, this is in the ballpark that everybody else is tending to report. But as we've seen, the rate of increase is very much dependent on the type of material applied. These are just some numbers from some work we did with David Paulson quite a few years back now, looking at long-term studies in the UK specifically. So these are UK figures. Farm manure compost, 60 kilos per hectare per year per tonne of dry solids applied. Could be potentially the topsoil carbon increase compared to biosolids a lot greater. But in terms of percentage retained, as we see, farm manure, the retention is a lot lower. It's about half what we can retain from the biosolids and the composts due to the stability and the decomposability of those materials. But I would caution, really, there's a lot of caveats here when we're talking about organic materials and soil carbon storage, particularly thinking about taking carbon out of the atmosphere and using it as a climate change mitigation practice. Is it genuine carbon sequestration? And as I say, there's a lot of different caveats. The first one is really, how reliable are our estimates? And we need to consider here a number of questions. What is the control? What are we comparing our change in carbon stock to? If it's a control that hasn't received any fertiliser or any inputs, then actually we will see a bigger increase, and we will think that the increase is a lot greater than perhaps it would be if that control had fertiliser, for example. How long was the study? We see that rates change over time. So when was the measurement taken? And this is critical. What was the soil depth when we took the measurements? So are we measuring like for like in terms of the amount of soil that we are sampling when we come to do these estimates of carbon storage? And then there are the limitations. Obviously, soils they have a finite capacity to store carbon, and the carbon they store, it is reversible, and often we see the losses, the rate of loss, it tends to be greater than the rate of increase, certainly when we see a ploughing up of grasslands, for example. And then we also need to think about the potential for pollution swapping. Do other greenhouse gases increase when we apply these materials? What's the full life cycle analysis here? And then finally, what's the alternative fate of these materials? If it isn't new, if we're already doing these practices, then it isn't new genuine carbon storage. It isn't over and above what we're already absorbing from the atmosphere. So, so we do need to think very, very carefully when it comes to thinking about manures and climate change mitigation. So just to conclude, I hope I've demonstrated that organic manures are a valuable source of organic matter and nutrients that can lead to improvements in soil health and crop yields. But we do need to be aware that not all materials are the same, and I think there's more work to be done there. And so significant changes in that functioning are really dependent on supplying sufficient organic matter that is biologically available. And we can increase soil carbon storage, but we do need to be aware of those limitations. And over it all, we do need to obviously consider the wider implications of these practices to improve soil organic matter so that we minimise any environmental impact. And that's me done. Thank you, John.
And that was fantastic. Thank you very much. That was an excellent presentation. And certainly it demonstrates the fact that you soils probably only have a finite amount of carbon they can store, and you're not going to keep going up and up and up by putting manures on. And also the interaction between other issues, particularly nutrient management, and making sure that we are able to manage the manures in a way which covers all issues relating to diffuse pollution and sustainable use of materials. Again, no surprise, we've got lots of questions which we won't all be able to answer in the time frame, but just got 3 that I'm going to pick out with the time. Does change in soil organic matter as a result of organic application vary with soil texture and or soil use management, etc.? And what is the best combination of soil type, so land use, to use? So I guess where's the focus?
Where are the winners? Where are the winners? Obviously, yeah. Really, we could do with a nice matrix of where to apply what material under what conditions, and that is something that would be really useful to try and do. Texture does obviously have a big effect, not only in the amount of carbon that can be stored within the sandy soil compared to a clay soil. So obviously sandy soils have a lower capacity to store carbon compared to clay soils. But actually it's on those sandy soils where we do see the benefit of having improved organic matter. So if we can improve the organic matter on those sandy soils, which tend to have problems with water availability and that kind of thing, that would be our target if we can. Yeah. So that's a very simple answer to what is a complex question.
Yeah, and get the application rates and timings right so you don't increase the nitrate leaching losses, I guess.
Precisely, yes.
Or the phosphate issues as well.
Yes, obviously those sandy soils are the most vulnerable for that from that perspective as well. So, yeah.
Yeah, good balance in that.
It is a balancing act.
Is it possible that changing land use I think this question relates to land use change, clearly. Are all land use changes going to increase organic carbon more than soil or than organic matter applications, I think?
Not necessarily.
Which land use?
To tell you the truth, I don't know the answer to that fully, but I would say that not all land use changes would necessarily be as beneficial and maybe as quick, for example, than applying a bulky organic material, highly stable organic material. And there are obviously some land use changes which are clearly detrimental in terms of carbon. You know, I gave the example of ploughing out grasslands. Returning to a grass lay arable, you know, there's questions about putting rotational grass in. The increases are very, very small in terms of carbon. They do tend to creep up, but it's slow. So maybe in those situations, applying an organic material would give you a quicker win. So yes, there are circumstances probably, but actually putting something down to grass is probably, for permanent pasture, is probably the thing you wouldn't do. Yeah. But then actually you need you're using the grass and you're bringing ruminant animals into the system, and what impact is having there. So, you know, we do have to look at it in the whole. in the whole.
Absolutely. Great answer. Great. So, and finally, how do you quantify topsoil microbial biomass? What's the method?
Yeah, so that method, there's a number of methods, but the method that we use was the chloroform extraction method. I think it's the gold standard for measuring microbial biomass. There's lots of other measurements that sort of compare to that measure. Basically, fumigate the soil and measure the change in carbon content as a result of that fumigation process. So that's the method we use there.
Brilliant. Thanks, and I'm sorry we're going to have to move on for
That's all right.
for the
Thank you.
Time. Otherwise, we'll be here until next year probably.
Thank you very much.
Thank you ever so much for that. Before I move on to Dave, I just wanted to say for our UK listeners that we've applied for basis points for this webinar, which is actually 2 basis points, so we've done well there. And all we need for you to do to claim those basis points, if you write your full name and the basis account number, that's the one that starts with 200 or whatever on it, in the questions tab, and we'll send those off to basis for you. So that's for our UK listeners only. Grand. Well, last but by definitely no means least in our presentation today, we're moving now on to Professor Dave Chadwick, who is based at the University of Bangor in beautiful North Wales. And Dave, you are going to talk to us about a manure management network and the activities that they're up to. Over to you. The floor is yours.
Many thanks, John. Hello, everyone. Yes, my name is Dave Chadwick, and I'm an agriculture and environmental scientist at Bangor University. My research career is really focused on the sustainability of different farming systems, and I've spent many years, more than I care to remember really, exploring strategies to improve nutrient use efficiency from manures and from fertilizers, and strategies to reduce greenhouse gas, ammonia emissions, nitrate leaching, etc. So that's a little biography of me. I'm now going to move on to the slides. So, first of all, we are really grateful to have this opportunity to raise awareness of this manure management network. It's actually part of the Global Research Alliance on Agricultural Greenhouse Gas Emissions, and the focus of the network is to provide a global forum for scientists who are focusing on reducing greenhouse gas emissions from livestock production, and look at the increasing the nutrient efficiency of manures by the improvement of excreta management. It's not a new network. In fact, it was officially started nearly 10 years ago now, and has subsequently had a number met in a number of places. One of the more important meetings was at the FAO in Rome, where we discussed what the key priorities of the network should be, and how we would link with other international activities that aligned with those priorities. There have been subsequent meetings. There's no actual funding really for the maintenance of this particular network. It's all born about, voluntary contributions, etc., by experts with a real passion for trying to promote improved manure management and reduced emissions. So we've always had meetings on the outskirts of particular conferences, particularly the Greenhouse Gas Animal Agriculture Conference, and the meetings in Dublin and Melbourne were really influential in developing the scope of the network and thinking a bit more about what those priorities were. But since then, there's been a bit of a lapse in activity, and earlier this year there seemed to be some appetite for reviving this a little bit and seeing whether there was a wider appetite for renewing the activities within it. And so currently the co-coordinators of this network are Professor Donghong Min from the Chinese Academy of Agricultural Sciences in Beijing, and Dr. Tony van der Weerden from AgResearch in New Zealand. And the current scope of the network is to address the challenges of adopting standardized measurement and modeling approaches across the global scientific community to enable more data sharing and comparisons of data and information from studies across the world, and to quantify and mitigate greenhouse gas emissions from what we're calling the extended manure management chain. And I'll explain that a little bit more in the next slide, but those of us who've worked on manure management for many years will be familiar with the sort of housing, storage and field application components of phases of the manure management chain, but we thought it important to include the grazing component as well, and I'll go on into that in a bit more detail later. Another important scope is to identify and address potential trade-offs and of course the co-benefits of greenhouse gas mitigation. It was recognized quite early in our discussions, back in 2015-16, that focusing purely on greenhouse gas mitigation was a little bit too narrow, because we're aware that trying to control this leaky nitrogen cycle in particular within the manure management chain means that we could potentially either exacerbate another pollutant pathway, but hopefully importantly identify co-benefits. So it's important that we address not just nitrous oxide and methane, but also the impacts of mitigation strategies on ammonia volatilization, nitrate leaching. And in general, the overall scope is to promote the sustainable manure management practices that improve the nutrient utilization. We've heard already from Karl Richards about how improved nutrient use efficiencies can result in reduced emissions. So it's a win-win really. So we can explore improved nutrient utilization and soil organic matter, we've just heard from Anne there, and also reduce environmental losses. So this slide is just a schematic really to explain the extended manure management chain. As I say, we're familiar with the housing, the storage and the field application components of manure management. And as Zhaohai mentioned very early on in his presentation, it's important to retain those nutrients through each of these phases to optimize and improve the potential for the nutrient use efficiency, particularly of nitrogen, when we come to apply that manure in the field, as long as we take good care and good practice of the manure application and don't lose all that benefit that we've accrued by, for example, just surface broadcasting and losing ammonia. But we also heard from Karl that an awful lot of livestock are reared outdoors or have access to the pastures for certain periods of the year, and that excreta that they deposit during grazing, the urine in particular, is a significant source of nitrous oxide. So including the animal and in the grazing component within the manure management chain seemed a very, very obvious extension of the scope of this network. So what do we hope to deliver? Well, we believe it's important to try and harmonize experimental protocols across the world for measuring nitrous oxide, methane and ammonia fluxes from each stage of that extended manure management chain to enable us to share data, share information in a more robust, scientifically robust way. We also want to develop and deliver a list of mitigation strategies that are applicable to a greater number of countries, climates, soils, and agricultural systems that are underpinned with an evidence base where possible. Those of you who are modelers or who have attempted meta-analyses of mitigation strategies for greenhouse gas emissions from manure management will be quite frustrated probably about the number of journal articles that you've had to exclude from your analyses because they just didn't report all the data that you needed to make that analysis scientifically robust. So, it's really important that we try to generate a minimum list of reporting for greenhouse gas flux and metadata for future journal articles to enable improved data sharing. Because we're interested not only in the greenhouse gas emissions, but also the utilization of the manure nutrients, it's important that we have a consistent approach to quantifying the fertilizer replacement values of these organic resources. So that's another important protocol we'd like to try and harmonize. And of course, the important thing here is trying to influence policy and guidance for improving manure management that helps to deliver to regional legislation and to national targets, and of course supports the Sustainable Development Goals. So we're acutely aware that there's many different international projects that are taking place now, subsequent to the start of the Manure Management Network, that align very well with it. So it's important we do recognise this and work alongside these projects where possible. I'm just highlighting two here. DataMan, which is a Global Research Alliance flagship project. This project aims to provide access to the most up-to-date knowledge on managing manure greenhouse gases. One of its primary focuses is to develop a database of greenhouse gas and ammonia emissions from each of the phases or stages of manure management, the housing, the storage and the field, generating a database of cumulative fluxes of emission factors to help identify mitigation strategies and to improve inventories. And the field database, or the database of the greenhouse gas emissions from field applications of manures, is now available. That's the website you can see there, and the project team are now working on the housing and storage databases. MELS is a FACE funded ERANET project led by Barbara Ammon, and this project just goes a next stage on from the DataMan. It actually takes those data, those new emission factors, and the understanding of the controlling factors that drive those emissions, to incorporate them into existing and, where needed, new decision support systems that can help address the cost effectiveness of mitigation strategies. So they're two projects that align very closely with the Manure Management Network as it stands now. So the future priorities and the new opportunities that we see, well, first of all, we recognise that Manure Management Network is currently limited to just a core group of countries that met in early 2020 after a period of very limited activity. So the future priorities are clearly to try and grow the network beyond the core group, and identify the priorities, which I've already highlighted, but there may be new priorities that come out of the result of this presentation and raising awareness of the network. Clearly, we want to identify the need for experimental protocols that are harmonised across different studies throughout the world. We want to encourage researchers and policymakers to utilise knowledge and data within the Manure Management Network, including, for example, that DataMan database. There's a great opportunity to extend beyond existing projects like DataMan and MELS to strengthen the data sets they already have acquired, to expand those data sets across different countries with a range of soils and climates and agricultural systems with different manure management. So there's a great opportunity for the network to help facilitate that. As I mentioned before, we do need to update or provide this list of minimum reporting of greenhouse gas flux and metadata for future publications that will facilitate future meta-analyses and modelling. And clearly, we need to identify funding opportunities that support some of these Manure Management Network activities on greenhouse gas mitigation, on improved harmonisation of measurement methods, and increasing manure nutrient use efficiencies. So look, if I've whetted your appetite even only a little bit, please take a look at the website. It's there. That will be updated in due course as we start to move forwards and progress the network. Please also feel free to contact the coordinators, Professor Dong Hong Min and Tony van der Weerden. Tony actually is also the lead, the PI of the DataMan project, so if you've got specific questions about that, I'm sure Tony could help you there. Or myself, I'm very happy to take emails, requests for information as well. So I think that's about it. Thank you, John.
Thank you, Dave. Excellent, brilliant. Thank you very much for that summary of the Manure Management Network. It's nice to see these different activities going on behind the, whilst in between RAMIRAN meetings and all the rest of it, an opportunity hopefully for you to be able to report at the RAMIRAN meeting when it takes place. Got one question from about the ALFAM database that has recently been updated, and just for information, that's from Sven Sommer. and new data are needed as well. So just to bring that to attention, that the Alfam database is there and available for being included.
Yeah, absolutely. I think the great thing about the network is that there's the opportunity then to expand that database and that Alfam model across, as I say, different climates, different soils throughout the world. At the moment, I think it's probably quite North European sort of focused, because that's where it's had to be. Yeah. The same concept could be used in other parts of the world.
No, exactly. And this is what the benefit of the network is being able to understand manure management practices from different parts of the world and see how practices that are used in one part of the world may be transferable to others, etc., etc. So it's a really positive meeting. And one last question. Is there exchange between the Manure Management Network and the INMIS project led by Mark Sutton? Is that ongoing?
There is by individuals who are currently on the Manure Management Network and in the INMIS as well. There's not really any direct alignment yet of the network with that project, but there are individuals who cross over both. That's one of the things that we need to work on still.
Brilliant. Okay, but yeah, I mean, it's developing and making sure and ensuring the communication, contacting people, working with the websites and all the rest of it, just to make sure that people are involved with any initiatives that are happening and publicising them, isn't it?
Yeah. So please get in touch, everyone.
Brilliant. Yeah, excellent. So on the presentations, we've had to change the web links to photographs because just in case the presenters clicked on the web link by mistake. So please don't, if the web link doesn't work on the recording or whatever, that's why. Okay, so basically you need to log into the website or use the web address to get onto the websites. Brilliant. Well, thank you very much, everybody. I hope you've enjoyed the presentations today, and on behalf of the RAMIRAN 2020 Organising Committee, I'd like to thank you all for attending today. I also hope it's given you a flavour for the RAMIRAN conference and that we are able to meet up in Cambridge in person sometime soon. At the moment, we're still planning to hold the conference in September next year, but clearly we are in uncertain times and we're not obviously certain about what's going to be happening. So we'll make more firm decisions early in the new year. So please can you check the website for updates, and that's the ramiran2020.org. But yeah, we're really looking forward to holding the conference when we can. I'd also like to clearly thank the presenters, all the presenters, for excellent presentations and for keeping to time largely, but also a really important thank you to Jane Rigby and Katie Trafford, who have kept us the technology working all this morning and without any hassle whatsoever. So thanks very much, everyone, and come to Cambridge. See you next year. Cheers now.